Okay,
has it started? I don't think it has started.
Yeah. It's a recording via the
I see. Okay, great. So the first talk today is by Emanuel Malek from Humboldt University in Berlin, and he'll talk about generalized geometry, consistent truncations, and the KK spectrum of string compactifications. Please take it away.
Okay, thank you very much. So indeed, I'll follow on today from Dan's talk yesterday, talk a little bit more about how we can use generalized geometry to understand what kind of theories can arise from consistent truncations. And then I also want to talk about how this actually gives us a very powerful new tool to understand to compute the Kaluza-Klein spectrum of large classes of string compactifications, including some which have few or no remaining symmetries or even supersymmetries. And this is based on work done in collaboration with many people. I won't read out all of their names, but they're all given down here. Okay. So I want to start with the question of how and when can we study a compactification using a lower dimensional theory when the compactification does not have scale separation. And in particular, this is something that arises in, I'll say, at least most ADS vacua that we know in string theory, and is even conjectured to be an issue for all ADS vacua. And for example, if we look at ADS 5 times S5, the vacuum of type 2b string theory, we can compute the full mass spectrum, and we know that there is no scale separation between the ADS scale and the compactification scale. And in particular, there is no mass scale above which we can integrate out modes to obtain some lower dimensional theory. However, we can study ADS 5 times S5 and type 2b string theory using a 5-dimensional supergravity model, which only depends on these 3 modes that I've circled here in red, which make up the 5-dimensional n equals to 8 gravity supermultiplet. So this is obviously not an effective theory that comes from integrating out some massive modes. But what is it? It's in fact a consistent truncation, like Dan Waldron discussed yesterday. So in particular, we can use this 5-dimensional theory to construct solutions of the full type 2b string theory. In particular, a consistent truncation is defined. The consistency is this requirement that any solution of the lower dimensional theory is also a solution of the full 10 or 11 dimensional theory. But why am I talking about consistent truncations then in the Swampland workshop? I mean, on the one hand, it's because the organizers asked me to, but there is maybe also a more direct connection to the Swampland. In particular, if you really insist that no ADS vacua have scale separation, then the only way that a lower dimensional theory with an ADS vacuum can come from 10 or 11 dimensions, and in particular string theory, is via a consistent truncation. And I think this fits in nicely with the usual picture in the Swampland, where you can write down a lot of theories that seem consistent in lower dimensions. In particular, in this case, you can write down a lot of so-called gauge supergravities with ADS vacua in lower dimensions, but only a small handful of them can be uplifted to 10 or 11 dimensions. And these are the ones that come from consistent truncations. Now, there are, of course, differences to a Swampland picture. I don't know what I should really make of this z-axis. This is usually the energy scale. These are not effective truncations, but certainly there seems to be some picture here where there are lots of models I can write down in lower dimensions, but only a handful of them are connected to string theory. Okay, so today I will briefly recap and build on what Dan said yesterday and discuss how to construct consistent truncations in generalized geometry. I want to then show you how this gives us constraints on what kind of theories can arrive from these truncations. And then finally, I want to tell you about some amazing new things you can do with generalized geometry. In particular, everything I talk about at the beginning is about how to look at theories which rely only on these modes that you keep in the truncation. I will then tell you about how to actually use generalized geometry to learn information about the other modes that you haven't kept in the truncation. Okay, so to recap some of the things that Dan said yesterday, when we're looking for a consistent truncation, we want to find some way of embedding in a nonlinear fashion a lower dimensional theory into 10 or 11 dimensional supergravity, we in particular require that any solution of the lower dimensional theory is also a solution of the higher dimensional theory. And this is, in general, a very hard problem and extremely tricky because the equations of motions are highly nonlinear. And like Dan already mentioned yesterday, symmetry arguments are crucial in making this work. So in particular, the classic setup for consistent truncation comes by looking at a group manifold. This is known as a Schwarz truncation, and there one uses the fact that one has a global set of well-defined vector fields, the left invariant vector fields on the group manifold. So in particular, these define a frame, a d by d invertible matrix, and crucially, the Lie bracket coming from the Lie derivative of these vector fields closes with structure constants given by the Lie algebra of the group manifold. And these two conditions together guarantee that we have a consistent truncation. And in particular, we can then define the truncation just by expanding all of our fields of the higher dimensional theory in terms of this the set of well-defined vector fields, our frame. But then there are other truncations that are consistent, in particular in 10 or 11 dimensional supergravity, that don't seem to appear from group manifolds. For example, there's the famous truncation of 11 dimensional supergravity on the 7 sphere constructed by De Wit and Nicolai in the 80s. However, this is again what Dan Waldron was saying yesterday, all of these different kinds of consistent truncations can be understood by generalization of a group manifold coming from generalized geometry. So in particular, we might have a consistent truncation that looks miraculous in 11-dimensional supergravity. So some miraculous things seem to happen with the equations of motion on some very complicated geometry with fluxes that somehow gives us a consistent truncation to lower dimensions. But all of these miracles can be understood in generalized geometry by unifying the metric and flux degrees of freedom and rewriting 11-dimensional supergravity in this generalized geometry language. We actually see that these very miraculous truncations are actually just truncations on generalized group manifolds. And what do I mean by this? I mean that we have a set of globally well-defined generalized vector fields in generalized geometry. So in particular, now we get a frame field for the generalized geometry. So these set of generalized vector fields form an EDD matrix element. And in particular, now again, they form some closed algebra, not under the usual Lie derivative, but under the generalized Lie derivative. And then the structure constants of this algebra tell us what the gauging is of the lower dimensional supergravity. And then finally, the truncation ansatz can also be written in a nice compact way, where we just expand all of the fields in generalized geometry in terms of this global set of generalized vector fields. Okay. Now, this generalized group manifold truncation will always give us a lower dimensional theory that preserves all of the supersymmetries of the original theory. So for example, here, this would give us in 4 dimension an n equals to 8 theory. But there is a way to generalize this to more complicated setups. And this is using what Dan introduced yesterday, where you define a generalized G structure. So if you have a generalized G structure on a compactification, you can, and you impose the fact that what's known as the intrinsic torsion contains only singlets under G, then you have a consistent truncation which preserves some smaller amount of supersymmetry. This is quite abstract. What does this mean in practice? It means that you need to have a set of well-defined generalized vector fields, which are stabilized by this group G, which is the subgroup of the exceptional group. So these would typically consist of some generalized vector fields, maybe some other generalized tensors. And then this condition of having intrinsic torsion, that's a singlet. Essentially, it means that any derivative operator you can write down that does not involve a connection, any of these has to close. So you can expand any of these back in terms of your set of well-defined generalized tensors. So for example, the generalized Lie derivative of any of your generalized vector fields should close into an algebra, and this algebra would define the gauge algebra of the lower dimensional theory. Okay, Now, these facts, even though they're quite abstract, actually tell us a lot about what kind of theories can arise from consistent truncations. In particular, we get constraints on the types of matter multiplets that can arise and the type of gaugings we can have. Okay. So maybe before I go into this, let me just briefly stop to see if there's any questions about this slight recap of what Dan Waldron was saying. Okay, then I'll continue. Please interrupt if there's any questions at any point. So there's some very generic features we can extract from this construction. So for example, one can show that the scalar manifolds that arise in these lower dimensional theories are always symmetric spaces. This is of course true if you had a lower dimensional theory with enough supersymmetry, then the scalar manifold by supersymmetry has to be a symmetric space. But if you don't have much supersymmetry, for example, n equals to 2 supersymmetry in 5 dimensions, then in general, the scalar manifold does not have to be a symmetric space. But if it comes from a consistent truncation, we can show it actually has to be a symmetric space. And in particular, the symmetric space can be computed, and it's always given by the commutant of the structure group within the exceptional group divided by the commutant of the structure group within the maximal compact subgroup of the exceptional group. Okay. And then moreover, another thing that you can show from this singlet intrinsic torsion condition, you can show that actually the compact part of the gauge group in lower dimensions always is realized by killing vectors on your compactification. And now these features allow us to say some very general things about which theories can arise this way. So for example, if we look at theories which preserve half of the number of supersymmetries in 4 dimensions and higher, then one can show that the structure group that's needed is a spin group, and it's always spin 10 minus d minus some number. So if this number n here is 0, then you get a pure half maximal theory in lower dimensions. If this number n is non-zero, then you get n vector multiplets coupled to this half maximal theory. And then you can see straight away from here, there's an upper bound on n. N is necessarily less than or equal to 10 minus the dimensions that you're ending up in. Okay. And similar considerations, you can also play with different amounts of supersymmetry. For example, n equals to 2 supersymmetry in 5D, and you get various bounds on how many multiplets you can keep. Okay. This is very algebraic so far. This is just about a general consistent truncation. If you now ask that this consistent truncation contains an ADS vacuum, then you can be much more constraining. So in particular, lower dimensional theories that have ADS vacua, or supersymmetric ADS vacua, you can now impose very strong constraints on which of these can arise from higher dimensions. So for example, again, in 5 dimensions, with half maximal supersymmetry, from the previous considerations, it looks like you can have up to 5 vector multiplets. If you now look for 5D theories which have also ADS vacua that preserve all of these 16 supercharges, then you find, in fact, you can have at most 3 vector multiplets and only a handful of different kinds of gaugings. I won't go into the full classification, but in particular, this is a useful tool, and you can exclude various low dimensional theories, which, for example, include some, I'll say, exotic or interesting RG flows. We can show that many of these cannot come from higher dimensions, at least not via consistent truncation. Maybe a more interesting playground is given in 3 dimensions. As usual, the lower down you go in dimensions, the more things you can do. In 3 dimensions, the maximally supersymmetric supergravities, they can be, well, quite exotic. In particular, you can gauge very, very large groups, even all of E8 or SO8 times SO8, and these all have ADS vacua. But you can show that all of these huge gauge groups cannot come from higher dimensions. In particular, the largest compact gauging always has to be a subgroup of SO9. Yeah. So here you can very easily see that generalized geometry tells you a lot about which kind of gauge supergravities can come from higher dimensions. Maybe one interesting question for this workshop is there a relation between these kinds of constraints and constraints that come from other Swampland conjectures? Okay. any questions about this first part of the talk? Okay, so if there's no questions at this point, I will continue. And now I want to tell you about how you can actually use generalized geometry to learn about the fields that you are not keeping in the consistent truncations. In particular, how you can compute all of their masses. So what does a consistent truncation buy you? Well, what we've known for a long time is that you have some low dimensional theory. For example, in ADS 5 times S5, you keep only these modes encircled in red. This gives you some 5-dimensional theory with an interesting scalar potential corresponding to different vacua. And you can, of course, compute the all of the properties of the modes that you've kept around any of these vacua, in particular, the masses of infinitesimal fluctuations. So, for example, you can go to some other vacuum corresponding to some complicated deformation of the 5-sphere, and you can compute how the masses change of the fields that you've kept in the truncation. But it seems that the consistent truncation loses any information about the other modes that you've not kept in the truncation. So now I want to show you can use generalized geometry to actually recover all of the masses of all the fields around any of the vacua arising from consistent truncations. And this is quite remarkable because in the traditional approach to computing these masses, the Kaluza-Klein spectrum, the traditional approach is very limited. So usually the only thing that can be done is to compute the masses of spin 2 fields around the general compactification. Or if we actually want to have the spectrum of all the fields, in particular the scalar fields, then we have to go to a very, very symmetric space, in particular a coset space. Here, this method using generalized geometry allows us to compute the full Kaluza-Klein spectrum for any vacuum arising from a consistent truncation to maximal supergravity in lower dimensions. And in particular, what makes this so powerful is that these different vacua you get from the consistent truncations, these can have very few or even no remaining symmetries or supersymmetries. So this gives us a tool for the first time to compute the spectrum around backgrounds that have, for example, no supersymmetry. Okay. So let me just briefly highlight why this approach with generalized geometry is very powerful. In the traditional approach, what you do is you expand any of your fields in terms of some linearized fluctuations on the background, and this linearized fluctuations you expand in terms of a set of harmonics on your background. So for example, if you had a scalar field, you would expand in terms of some small fluctuation times the harmonics in the background. In the generalized geometry picture, there's a much more natural ansatz than this, where rather than expanding the fluctuations just in terms of the harmonics, you expand it in terms of the modes kept in the consistent truncations times the harmonics. I'll explain this in detail in a little bit later. So in particular, what's so useful about this is that this Kaluza-Klein ansatz then is completely nonlinear in the modes kept in the consistent truncation, and of course linear in the higher Kaluza-Klein modes. But this means that we can perform the spectrum analysis first at some very symmetric point in the lower dimensional theory, for example, the round 5-sphere compactification. But then because we're nonlinear in the modes kept in the consistent truncation, we can also extract the spectrum around any other vacuum, which might have very few symmetries. Okay. So in particular, how does this work? Since I'm focusing on theories that arise from maximal supergravities and their consistent truncations, then we know from the previous discussion that you always have a generalized, a global set of generalized vector fields. So a well-defined generalized frame field. And this in particular then gives us a basis for all the fields in the supergravity in terms of generalized geometry. In particular, what this means, we can expand any fluctuation in terms of this basis of well-defined fields. And as a result, we can view all the fluctuations just in terms of scalars. We can just expand them in terms of scalar harmonics. And this should be contrasted with a traditional approach. So in the traditional approach, you would have to take each of the fields in supergravity and expand them into harmonics corresponding to their tensor structure. For example, the internal matching components from the compactification would have to be expanded in terms of a set of harmonics that are symmetric traceless. The two-form of type 2b, for example, would have to be expanded in some two-form harmonics. Here in generalized geometry, you already see a remarkable simplification, even for very symmetric backgrounds, where for all of these fields, you just need the scalar harmonics. Oh, sorry. And in some sense, that is maybe not so surprising, that something like this should exist. You might have expected. And this you could see as a manifestation of the fact that the n equals to 8 supermultiplet contains all of the supergravity fields. So because you can expand the scalar fields in terms of scalar harmonics, you might imagine that with n equals to 8 supersymmetry, somehow you should be able to expand all of the fields in terms of the scalar harmonics. And generalized geometry really realizes this, but in particular, as I will show, it allows you to use this information even for backgrounds which don't preserve any symmetry or supersymmetry. Okay. So in particular, if we look in generalized geometry and we look at fluctuations around the background, we want to understand fluctuations of the generalized metric that Dan Waldron introduced yesterday. And this is some element of the coset space E77 over SU8. So some small fluctuation of this object will be captured by something valued in the Lie algebra of E77 minus SU8. So for example, if you want to write down a small fluctuation corresponding to something in the consistent truncation, then you just write down your consistent truncation ansatz, and now you just expand your lower dimensional field to first order. And this then, as I said, is some element of the Lie algebra E77 minus SU8. But now you can expand this to a Kaluza-Klein fluctuation where you just say, okay, this is just some arbitrary scalar field. And you just make it, you just expand this arbitrary scalar field in terms of the scalar harmonics on the background. And this realizes what I said before. In generalized geometry, we can view any fluctuation in this form. And now you see that the Kaluza-Klein ansatz, it has this form of expanding in the consistent truncation, which is captured by these U matrices, which are a global generalized frame, times now the scalar harmonics around the given background. And in particular, this is not just philosophically nice, it also gives, it plays very well with the equations of motions of generalized geometry. And in particular, it gives an immediate mass diagonalization. And because it's nonlinear in the modes kept in the consistent truncations, you can use this to compute the masses very easily for any vacuum of the lower dimensional theory. So in particular, you get an algebraic mass matrix by plugging this ansatz into the generalized geometry equations of motions. And this algebraic mass matrix just depends on two pieces of information. The first is lower dimensional information. This is information of the supergravity model that you're using in the lower dimensions, in particular the gauging, which were these structure constants XABC coming from the generalized Lie derivative of the generalized frame on itself. And then the only other object we have are the scalar harmonics, and we just need to know how the generalized frame acts on the scalar harmonics. This gives a representation of the gauge group in the, this gives just generators of the gauge group in the representations by the scalar harmonics, which are labeled by sigma and omega. And these are the only piece of information that you need to write down now the masses for any vacuum of the lower dimensional theory. In particular, as I said, you get an algebraic mass matrix. This corresponds to 1 bit, which is just the lower dimensional mass matrix. So the mass matrix capturing the modes kept in the consistent truncation. This is just given by the structure constant squared in certain combinations. Then you have a bit which only acts on the scalar harmonics. And this comes from a Casimir constructed from these generators in the harmonics representations. And then you have a mixed term where this is this last term where you have some certain projection of X acting on this scalar, on these generators. And this is where all the interesting physics in the end comes from. Okay. So having done this, in particular, using the scalar harmonics around the maximally symmetric background, we can then also use this ansatz to compute the spectrum around any other vacuum of the lower dimensional theory. And in particular, all that one has to keep track of is multiplication by an E7 matrix corresponding to this deformation in the lower dimensional theory. And in particular, one very nice thing is that we do not need to recompute the scalar harmonics. We can use the scalar harmonics on the maximally symmetric background. Everything is just captured by this E7 multiplication. Okay, so let me just pause if there's questions about this general methodology, because otherwise I'll just continue with some nice applications of this.
Hi, I have at least two questions.
Sure.
First one is, it's about the mass matrix. Does it change if you go to a vacua with less symmetry?
No,
is it universal?
Right. So this mass matrix is universal. The only thing that you have to keep track of, the thing that keeps track of the lower dimensional theory, are essentially these indices A, B, C here, and I and J. I don't really want to explain what I and J are. Some combinations of A, B indices. So these are the E7 indices, and you just have to multiply these in appropriate ways by the E7 matrix corresponding to the vacuum. So even if your vacuum preserves no symmetry or no supersymmetry, the mass matrix has the same form. You just have to multiply all of the indices with this E7 matrix corresponding to the vacuum you're looking at.
Okay, thanks. I'll do the next in another time. Thanks.
Okay. Okay. Any other question before I continue?
So it's just very naive. Is it just a simple saying that because it's a consistent truncation, then it must be that all the massive states do not couple to the modes that are in the consistent truncation. And therefore, if you move around, if you change the expectation value, then the spectrum of massive states does not change, or
no. So the masses do change and they do couple.
Okay.
It's just that you can track all of the coupling by some smart E7 multiplication. So I mean, yeah, I've hidden lots of things. So for example, here you see in the spin-2 matrix, I have two A indices contracted. This contraction should be understood as happening with the matrix that corresponds to the lower dimensional vacuum. So this contraction would contain the information about what lower dimensional vacuum you're looking at.
Okay, thank you.
Yeah.
And so if I turn on fields that are not in a consistent truncation, then you
then
can't
I don't know. Then I can't say
Okay.
anything.
Okay.
Yes,
Thank you.
I can tell you everything about what happens as I deform with the lower dimensional modes. Okay, cool. Right, if there's no more questions at this point, I'll continue with applications, and please, continue interrupting if you want at any point. So the first application is looking at some supersymmetric ADS4 vacua in 4 dimensions. So there is a lower dimensional theory you can write down that has a family of n equals to 2 ADS4 vacua. This arises in some particular supergravity model. The details really are not important. But what's very nice about this model is it contains a moduli space of these n equals to 2 vacua. And in particular, these two moduli are phi and delta. For a generic point in this moduli space, the ADS4 vacuum preserves to C1 times C1 symmetry. But at special points, the symmetry enhances. So for example, in some particular set of coordinates, when the moduli are turned off, the symmetry group enhances to SU2 times U1, whereas at some other point, you have an enhancement of supersymmetry. So that's very nice in this model, but there's also some puzzles. In particular, in the 4-dimensional model, these moduli are non-compact. They can take any positive value. And this certainly clashes with various expectations about moduli space of CFTs. And for example, was also highlighted recently in a paper by probably people who are all here. So what's happening with these n equals to 2 ADS4 vacua, and can we use this technology to understand how maybe this moduli space is made compact? So firstly, this 4-dimensional model, it can be uplifted to type 2b supergravity, or maybe I should say type 2b string theory, and it comes from a compactification on S5 times S1. So any of these ADS4 vacua uplift to full solutions of type 2b string theory, which take the form ADS4 times S5 times S1. And they're S-fold type of vacua, but I don't want to say much. Well, I don't want to say anything about the S-folding, but of course you're free to ask at this point or later. And in particular, you can use this truncation ansatz that was worked out by these people to uplift any of these ADS4 vacua. And in particular, various people looked at these special points where the bosonic or supersymmetry group enhances. But still, how do we now understand what happens with the moduli space? Can we see what happens as we go to large values of phi and delta? And in particular, with a number of collaborators, I use this technology of computing the Kaluza-Klein spectrum to understand what happens as we change this phi modulus. Right. So in particular, with these lovely people here, we computed the Kaluza-Klein spectrum of these. So it should be ADS4 times S5 times S1 vacua as we vary this phi modulus. And in particular, we computed the full spectrum, but I'm just showing you this mass of one of the modes, some particular mode that I'm keeping, and this is the normalized mass, normalized relative to the ADS length. Plotted as a function of phi, where phi is also normalized with respect to the radius of this S1. And if you look at this a little bit, you see that it has some very nice pattern. Modes that seem heavy when phi is 0 appear. Some of them become light when phi goes to 2 pi over t, and some of the modes that were light end up becoming heavy as we go this way. And in fact, if you look at this for, well, maybe just a few seconds, you start seeing that it looks very, very symmetric around this point. And in fact, this is not just an illusion. You can show that the full Kaluza-Klein spectrum actually gets mapped to itself as we change phi to phi plus 2 pi over t. So what happens? What happens is the following. Whenever phi is an integer times pi over t, some modes that were amongst the higher Kaluza-Klein modes, not kept in truncation, become massless. In particular, as I said, for a generic point in this moduli space, the symmetry group is U1 times U1. But whenever phi is an integer times pi over t, you actually find that 2 extra vector fields become light, and these enhance the bosonic symmetry group to SU2 times U1. Moreover, the full spectrum is actually identical whenever phi is 2 pi over t, then the whole Kaluza-Klein spectrum is identical, and there's just some reshuffling of the fields between the higher modes and the lower modes. And then these vacua marked in blue, they also have this enhancement of the bosonic symmetry group, but there the spectrum really is different. So these are really distinct vacua from this red one and the green ones. Okay. Now you can then also use the full truncation ansatz and understand what happens to the modulus. And you see that this, the fact that the modulus seems to be any positive number, this is just a 4-dimensional artifact. This is just something that comes from the 4-dimensional theory because you've kept only a subset of modes. Once you take into account the full set of modes, phi actually becomes compact and takes values between 0 and 2 pi over t. And you can really understand this from the full 10-dimensional geometry. I won't go into much details, but you can really understand this modulus phi as some complex structure modulus on S5 times S1. And then this periodicity is extremely similar to a Dehn twist of the complex structure of a torus. Another way to view this is to view phi as a coordinate transformation. This is only locally well defined for arbitrary values of phi. But when phi takes a value,
is there a question? I think someone's just unmuted themselves.
Exactly. Anyway, so when phi has this value of 2 pi over t, then you can really absorb it into a coordinate transformation that's globally well defined. So that's a different way of understanding this periodicity. But you see very nicely that only once you take into account the higher modes do you see this expected compactness of the moduli space. Okay. So finally, let me just conclude with another example. So there were already a few questions about non-supersymmetric vacua. So let me talk about one such example. as I said, you can get a 4-dimensional theory by doing a consistent truncation of 11-dimensional supergravity on the 7th sphere. This 4-dimensional theory has a number of non-supersymmetric ADS4 vacua, but almost all of them are unstable in 4 dimensions already. Oh, I see a
There's a question by Nikolai.
Yeah, Nikolai, go.
Maybe you want to finish your sentence.
Okay, I'll finish my sentence. All of these non-supersymmetric ADS4 vacua are unstable in 4D except for one single ADS4 vacuum. And then, yeah, this particular non-supersymmetric ADS4 vacuum is a vacuum found by Nick Warner in 1983, corresponding to some very complicated deformation of the 7th sphere that only preserves SO3 times SO3. And then an interesting question is this also stable in the full 11-dimensional supergravity theory, or is there some instability? But I'll stop here for Nikolai to ask a question.
Yeah, hi. I just want to ask whether you are claiming that the full 2-dimensional conformal manifold is compact, because I kind of missed the punchline.
No,
you're talking about one of the.
I'm only talking about one of the lines, one of the directions. We are working on the delta direction.
Okay, good.
There is a paper that claims it's non-compact, but well, yeah. Let me just say we're working on it. So
that's the paper we wrote. That's why I'm asking if you have something to suggest that it's actually compact. That was my question.
Yes, but not to an extent that I should say here. We're working on it. I think it's compact, and I think we can show it. But we hope to write a paper on it in the next months. Okay. Yeah, maybe I should stop and just ask if there's any other questions about this 2D moduli space before I move on. Okay, then let me come back to this non-supersymmetric example. So now you can use the technology that we've used. Maybe I should just firstly say, why would you expect that there should be any kind of stability? Well, I guess if you have this intuitive picture in mind that somehow a consistent truncation corresponds to choosing some set of modes, and these are at least some light set of modes, and even though there's no scale separation, the other modes like an ADS5-5 are maybe equally heavily or heavier, then you would think if this is also true for the non-supersymmetric vacuum, the fact that these modes in the non-supersymmetric vacuum are above the Breitenluner-Friedman bound would suggest everything else is too. Now this is something you can test with our technology. So we computed the masses of all of these scalar modes in particular, and I'm just going to show you the lowest lying modes. And this red line here is the Breitenluner-Friedman bound. This is the mass basically, and this here is, well, it counts the SO3 times SO3 representations. So the n equals to 8 supergravity modes, these are the level 0 modes. These were computed in 2010. These are stable, as I said. But now we can compute the level 1 modes. These are still stable, even though already they're not as you would expect. They become lighter, and some of them become dangerously close to the Breitenluner-Friedman bound. But then at level 2, you see that actually some of these higher Kaluza-Klein modes actually become so much lighter that they become tachyonic. And then eventually you can continue, you can compute the masses at higher and higher modes, and you do find that eventually the spectrum seems to behave as you would naively expect. Eventually the masses increase with mode number, but not at the first couple of modes. And as a result, some of the higher Kaluza-Klein modes are actually tachyonic. So even though this ADS4 vacuum appears perturbatively stable in 4 dimensions, it's actually perturbatively unstable in 11-dimensional supergravity. Okay, I'm quickly running out of time, so I'll not say much. I'll just say there are some other examples of non-supersymmetric ADS vacua that are actually also perturbatively stable in 10 dimensions. They might have other issues, but at least perturbative stability sometimes works, but not in this particular example. Okay, so let me conclude. I've shown you that we can use generalized geometry not just to construct consistent truncations, but also to exclude theories that cannot come from consistent truncations. And we can also now compute the full spectrum of Kaluza-Klein fluctuations around any vacuum arising from consistent truncations. And let me just, well, maybe 3 interesting themes that have arisen. If you assume that there's no scale separation for ADS, then many gauge supergravities don't seem to have a higher dimensional completion. So perhaps one should call these as belonging to the Swampland. I've also shown you 2 different examples that the higher Kaluza-Klein modes in the consistent truncations can be absolutely crucial for the physics. For example, compactness of the modular space and stability. And we can now actually compute this. And then just a final mention, if you're interested in ADS CFT, then computing this Kaluza-Klein spectrum is very interesting because it tells you about the anomalous dimensions of the operators in dual conformal field theory. In particular, you can compute the anomalous dimensions of unprotected operators, not just the protected one. And I had a very fun collaboration with these people here where we did this for the Lee-Strasser theory, and then also checked with the superconformal index, and the protected operators match quite nicely. The unprotected ones are obviously a prediction you get then from supergravity. And let me end here and thank you for your attention.
Okay, thanks very much. Let's thank Emanuel for his nice talk. Are there questions? We already had a few questions. So Thomas, I guess, van der Riet is raising his hand.
Yeah, I think I have more like a comment about the last slide. So I think there are gauge supergravities which have a clear 10-dimensional origin, but which are still in the swampland. And I don't think that that's a contradiction. It's more related to what we mean by the word swampland. In particular, I'm thinking of those gauge supergravities which have non-compact gaugings that tend to come from non-compactifications. And these non-compactifications nonetheless allow a consistent truncation to a lower dimensional supergravity. Yet they violate any possible swampland constraint that we know of, right? And I think the only reason is that because the cutoff is actually at 0 energy, right? And so I'm just saying something here about language, which can be confusing to outsiders. That's all I want to say.
No. It's actually a very interesting point. And I think this is probably also related to something Miguel spoke about yesterday. It's very hard to know how we should think about these gauge supergravities that can or cannot come from consistent truncations, because there is no separation of scales. There is no low energy theory that these belong to. So yeah, even saying swampland, exactly as you say, it's not really clear what one means. It's not like these work up to some energy scales and at some energy scales things break down. So maybe somehow one should think of this as the swampland of massive modes as well, like Miguel
but maybe a concrete difference could be that, at least in the case of ADS vacua from compactifications without scale separation, there's at least a gap. And the only problem is that the gap is of the same size as the masses in the gauge supergravity, but at least there's a gap. For the non-compact gaugings, there's not even a gap. You see, I think that is a difference. It's a continuous spectrum, and that is really the problem. Yeah.
Yes.
Okay, thanks. Joseph.
Hi, Manuel. I just wanted to ask you if you have. So I have only seen the phenomenon you discovered with this masses, with this max spectrum, which actually becomes, just changes and goes back into itself, and basically some levels go into some other levels and so on. I have only seen it once in my life when I was doing massive 5-dimensional n=1 theories. But there, for example, if you look at the deforming theory, you put some masses, and then as you increase the mass for some special values of the mass, you find that again the spectrum shuffles back into itself. But there was a very clear reason that if you see these theories from an M theory perspective, basically they are given by some M theory compactification with a Melvin twist. And when you have a Melvin twist, you're basically compactifying M theory, and when the twist becomes 2 pi, you are basically having the same compactification, but the spectrum shuffles into itself completely, and you get exactly the same reshuffling as the one you found. I'm just wondering if there's a relation. I mean, can we see this shuffling of the levels as coming from some sort of similar to the Melvin twist, or is it? I mean, maybe I didn't catch the
No. It is. I'm not 100% sure what the Melvin twist is, but it sounds very, very similar to what.
You're compactifying basically to 10 dimensions, but you're not compactifying on x11. You're compactifying on x11 plus alpha times phi, where phi is the angle.
Yes. So this is this is very similar. So, okay, there's a way to make this more concrete. So in this case, because you have, so it's best to think about this in terms of this SU2 times U1 theory as the deformation. So this SU2, you can think of as coming from some 3-sphere inside the S5. So you can view this as a 3-sphere fibered over S2. The 3-sphere, you view that as a Hopf vibration. So the Hopf fiber of that 3-sphere together with the S1 make up a torus. And the complex structure on this torus, its real part is exactly phi. And there then you see exactly this shift in phi is exactly the twist. And that's exactly like what you're saying with the Melvin twist. So this you can really understand in the same way, but it's indeed, it's something which you don't see in the 4-dimensional theory because you've only kept a subset of modes that become massive and you haven't kept the modes that become light.
Cool.
Okay,
thanks.
Luca.
Hey, hello. Yes, I have a related question. So, a curiosity, does this reshuffling of degrees of freedom appears as a self-duality of the 4-dimensional theory, or?
Yeah, I mean, it's not clear what you mean by the 4-dimensional theory. I guess the 4-dimensional theory here, this SO6 times SO11 seminar product R12, you don't see any sign of the compactness there. So if you want, you've kept this dark blue line.
I mean, you said that when you reach this I mean, you go through this interval at the other end point, you can reshuffle degrees of freedom. I was just wondering if you can see it as a kind of self-duality or the same gauge supergravity, or do you map that supergravity to that consistent truncation to another one?
I guess that's not true, right? Because it's only in one of the parameters that you have this.
Yes. In some sense, I mean, I guess you're asking, should I view as when I go to phi goes to 2 pi over t, should I just view this as it's just bringing me back to the same supergravity, but with phi is 0?
Yes, that was my question, yes.
Yes. I think you can say that along one of the directions. It's much less clear what happens with the delta direction. So this phi parameter is axionic. And it corresponds to this kind of twist. The delta is much more complicated. This is more like a radial deformation. So there, it's much less clear what one should make of it. But I think, yes, I think with the phi, you can, I'll have to think about it a bit more carefully, but I think you can probably interpret it as the way you're suggesting.
Okay, thanks a lot.
By the way, are you supposed to think of this as this periodicity exists for any value of delta, or just a delta equals to 0, I guess?
We know this exists at any value of delta, this periodicity. But in this paper, we're only looking at strictly delta equals to 0. But by now we know this exists for any value of delta.
Yeah, I think we might need to move on. Joseph still has his hand up. I guess this is a quick question.
Oh, sorry, I forgot.
Macarius, you want to?
Sorry, I forgot to lower it. Sorry.
I think you asked the question before already, but if it's quick, let's do it.
No, I forgot to lower it.
No, not you, Joseph. Is there somebody else?
Yes, the question is quick, but I don't know about the answer.
Okay.
I'll try.
Let's see.
Well, it's just to understand a little bit more about the deformation you do when you go from the maximal symmetric point to another vacuum. I just want to understand a little bit more the meaning of the deformation. I mean, I don't know if all the vacua have to be the same topological structure. It's just
right. Yes. So I mean, any vacuum is obtained by continuous deformation. So they're all the same topology. In particular, one thing already that because these are consistent truncations